So in this lecture, we continue our discussion about integral extensions, but before that, we just need to define one notion of ideals called height. Okay. So for a prime ideal P of R, define height of P to be the dimension of R localized at P. Okay. And what is this? This is the supremum of L such that there exists a chain of primes, a chain of primes, P0 strictly inside P1 and PL, and that is strictly inside P. Here it could be equal, and in fact one should allow for equality in the supremum. Okay, so that is just because primes inside RP are precisely, they correspond to primes with this property. Okay, so these are strict inequalities, and here one would allow the last one to be equal to P. So such this is called height of a prime, and height. So this is this is height of I. Okay, so height of P. This is P. Okay, for an R ideal I, define height of I to be, which we denote by HT, I to be the infimum of height of P, where P is inside P contains I. Okay, so we define. So this is the height of an ideal. Okay, and for all P, height of P plus dimension of R mod P equals is less than or equal to dimension of R. Okay, so why is that? Height of P measures length, a supremum of lengths of a chain that starts from somewhere below a minimal prime and goes up to P. Dimension of R mod P will start from 0 of R mod P, and because it's a domain, 0 of R mod P, and then go up to a maximal ideal. But inside R, it is the same as starting from P and going to a maximal ideal. So on the left side, okay, this involves a chain of primes through P. Well, the right side doesn't. It could take any chain. So clearly, any chain that gets counted in this calculation on the left side also gets counted on the while calculating the right side. So we get, and this is a supremum. So we get this inequality. And it's a fact that this is not equality in general. In general, even for Noetherian rings. So even for Noetherian rings. Okay, we won't discuss such examples, but it is well known. It is known. Okay, there are books describing these examples. Okay, so that's okay. So in fact, that this is not necessarily an equality is one of the problems in trying to prove or that dimension of a polynomial ring in n variables over a field is n. Okay. In fact, this is true. The equality is true in those rings, but one needs to prove that first, or one would just be going in circles. Okay, so So just keep this. Okay, this is a notion that we need to use when we study ring extensions, ideals in general. Okay. So just a question about terminology. Some books might refer to this height as codimension, but it's a slight misnomer. So in the sense that it might give us the impression that we are talking about the difference of the dimensions. This is the dimension of some ambient space. This is the dimension of some subspace, and we're talking about the difference when you use the word codimension. So we will stick to you with the terminology as height. So one should just keep this in mind when. Some books do refer to this as codimension, but it can be because it is not equality here. They are not the difference between the dimensions is not the same as a height in general. Okay, so that's just a definition. Okay, so now what we want to understand is if you have an extension of rings R to S integral, well, just one point, if you have an integral extension from R to S, well, we saw from earlier lectures, it doesn't, what R is not really relevant for the problem. What matters is, so let's call this phi, okay, so integral extension, nothing to do with, in general, okay, so what matters when we study things is, okay, so what matters is this is the image of phi inside S. Okay, whether an element S is integral over R or whether all of S is integral over R, is S finite over R, all those conditions are tested for this image, not for what the ring is. Okay, you could add many things in the ring and then put all of them in the kernel. It is not going to affect the nature of this map. It is not going to affect the nature of the questions that we study when we look at integral extensions. Okay, so what matters is this. So hence we will assume that R is inside. Hence take R inside S. Okay, so this is what so our setup is R inside S. Integral extension, and we would like to understand this map a little bit better. Okay, so here is a lemma, and so this is a topic in commutative algebra where we see certain techniques come on and on again, which in the sense that localize, go modulo this, and this. Okay, this is one where many arguments one does localize this first or go modulo this prime ideal, then prove it, and that sort of thing. This is one place where one sees them for the first time quite a bit. Okay, so hence the following lemma is a sort of the base case for many arguments. Assume that S is a domain. Then R is a field if and only if S is a field. Okay, so we assume that S is a domain. We need to assume this. So just a remark: need to assume S is a domain. Okay, otherwise, K. This is a field sitting inside Kx mod x squared contradicts this assertion. Sorry, contradicts the assertion. R inside S, X is integral over it. It's even, okay? But this is not. This is a field, but it's not a field. The reason is that we didn't assume it's a domain. Okay, so. Let's prove of the lemma. Let so this is the if direction. If S is a domain, then R is a domain. If S is a field, R is a field. So let R be inside R but not 0. Okay. There exists S equals R inverse inside S because S is a field. So what does that mean? But this is integral over, okay. Therefore there exists an equation S to the n plus R Ri S to the n minus I goes from 1 to n equals 0 in S. Okay. So now let's multiply throughout by R. Rs is 1 of S, but R is a subring, so it's 1 of R also. So this gives 1 multiplied by R to the n. Okay, so this term gives 1 plus, and everywhere here there will be some term R, there will be an extra R term. There will be an R term for n minus 1, R square for n minus 2, and so on. R times I goes from 1 n of some Ri R n minus I minus 1 equals 0. Okay. But then this is an inverse. Okay, because the Ri is in R. So remember, this is inside R. That's the integral equation part, and this is inside R. So the sum is inside R. Okay, so this is satisfied. I mean, this sum is inside R, and this, so 1 plus R times an element of R equals 0. So therefore, R is invertible. Sorry, therefore R is invertible in R. Okay, so that's a few. Now only if. Okay. So let S be inside S. Again, there is some S, there exists some equation S to the n plus R1 S to the n minus 1 up to Rn equals 0 in S, Ri inside R for R. Okay. Now, among all such expressions, pick one with smallest n. So this is important. We pick the one in which the degree of this polynomial is the least. Okay. That's possible. Okay. So for that one, then Rn is 0, is not 0. Okay. Why? If Rn is 0, so Sn otherwise, okay, we can rewrite that as S times Sn minus 1 plus R1 Sn minus 2 all the way up to Rn minus n minus 1 equals 0. But S is a domain, and this is where it is used, and exactly this is the step which would fail in the example I mentioned above. S domain implies that there is an integral equation of smaller degree. Okay, so this is where domain is used. Okay. So now we can rewrite this. So this was the expression. So we can take Rn to this side, and then this is okay. So this similar way we write S times Sn minus 1 plus R1 Sn minus 2 all the way up to Rn minus 1 equals minus Rn. Okay. But this is invertible. Okay, so this is invertible. Okay, S times something is a unit, invertible in R and in S, because if it has an inverse in R, that will remain an inverse in S also. Okay, so S times something is invertible, so then S times something else would be 1. Okay, this implies now that S is a unit. S is invertible. Sorry, one can't prove S is invertible like this. Only non-zero. Where did we assume S is non-zero? Well, if S is 0, so we assumed S is non-zero to say that this n is at least something. If S is 0, then you would just get S equals 0, and then this argument won't go through. Okay, so let's be careful. S not equal to 0. In fact, that's the only correct statement. Okay, so this is every non-zero element is invertible. Okay, so this is the proof of that proposition, that lemma. Okay, so now we prove a proposition which tells us substantial amount of the morphism. Given an integral extension of rings, what does spec R to spec, what does a map on specs do? This following proposition gives us a good amount of information about that, okay, which is not true for many arbitrary morphisms. Okay, so proposition. Let P be in spec R and Q in spec S, so primes, such that let be such that Q contracted to R is P. Now, so this is the image of the map from spec S to spec R. The image of Q under that map is P. So this is point 1. Then P is maximal if and only if Q is maximal. Two, suppose we have two Q1 inside Q2 in spec R. So let Q1 inside spec in Q2 in spec R be such that they contract to the same prime ideal below. Q1 intersect R equals Q2 intersect R. Okay. Then Q1 equals Q2. Okay. So this is sometimes called, some textbooks might refer, at least informally, as incomparability. Okay. Two distinct Q's that contract to the same P below must be incomparable. If one is contained in the other, they must be equal. Okay. So that's what it's saying. Okay. There are two Q's in spec S. Okay. Two primes and points in spec S which map to the same point below with this property that they are comparable, then they must be equal. So this is sometimes called incomparability. And 3, this is sometimes called lying over. Okay. For all P in spec R, there exists Q such that Q contracted to R is P. Okay. So let's just briefly look at this proposition before we prove it. Proof is not very difficult. Okay. So just a note. Okay. 3 says that 3 says that the map spec S to spec R is surjective. Okay, so the finite surjective, and one says that fibers over maximal ideals, fibers over maximal ideals, ideals of R contain only maximal ideals, only maximal ideals of S, and every maximal ideal of S maps to a maximal ideal of R. Okay, so this one can think of this as so this one, for example, would apply in the case of Noether normalization. So this is one thing to so one nice property about these maps. Okay, so proof. As I said, the proof is not very difficult. It is just okay. So what are we given? We are given an integral extension of maps like this, and we want to prove that. So then we are given some Q inside here and a P inside here, and this maps to, I mean, I'm drawing the arrow not as a map of sets, but now think of it as a point inside spec S. Okay, so maybe I'll just like this. Okay, so this curly arrow here denotes the map in spec S in the opposite direction. Q goes to P. Okay, but Q is, remember, is just a point in spec S. Yeah. So this. So with this thing, we can look at S mod Q and R mod P. That's because P is Q contracted to R. This is again injective, and it is integral. So this if you have an integral extension, this is integral. If you have an integral extension there, and if you do this step, it remains integral. Okay. This also remains integral. Now this is a domain. Okay. And therefore R mod P is a field if and only if S mod Q is a field. Therefore R mod P is a field if and only if S mod Q is a field, and this is equivalent to saying P is maximal, and this is equivalent to saying Q is maximal. Okay. So this proves one. Proof of 2. Okay, so let's write P. So this is the statement where two prime ideals of S contract to the same prime ideal of R, and Q1 is inside Q2. Okay. And we want to show that that's an equality. Okay, so let's invert. Let's invert elements outside P. Okay, so we have R to S, and sorry, not an inclusion. This gives a map from R localized at P to R minus P inverted inside S. Okay, so this is, I mean, P itself, P extended to S need not be a prime ideal. Its complement, complement of the extension of P need not be multiplicatively closed. What we are inverting is just those elements of R that are outside P. Okay, so we invert this. So this is integral. Please check that this is also integral. Now P is a okay. Yeah. So P RP is a maximal ideal here. Is the maximal ideal there here. Okay. So notice that. So let's call this ring S prime. This local, after this inverting, call it S prime. Q1 okay, Q1 S prime contracted to RP is same thing as Q2 S prime contracted to RP, and this is just the maximal ideal P RP. Okay. Therefore, it must be a maximal ideal of this that contracts. This is maximal by one Q2 S and Q1 S prime. Q1 S prime and Q2 S prime are maximal in S prime, but Q1 S prime is inside Q2 S prime, but this implies, because both are maximal, it implies that Q1 S prime is equal to Q2 S prime. But using the correspondence between primes in a localization, and this one says Q1 is equal to Q2. Okay. So all that is being, so we localize here, and then we are now looking over things that map onto the maximal ideal here. Therefore, the primes here also must be maximal ideal in the fiber, and but then there cannot be a strict containment between them. Okay, and this is preserved under localization, so you can go back to the original case. Right. Okay, so 3. Okay. Yeah. So now again we have R2S, and then we have a map to RP. Yeah, to again the same ring, R minus P inverse S. Okay. This is again integral, and we observed that a maximal ideal here can only contract to a maximal ideal here. Okay. So every maximal ideal of R minus P inverse S contracts to PRP, which is the unique maximal ideal of RP. Okay. And but then, okay, so let's go back to this diagram. We have a maximal ideal here which contracts to PRP here, and here it would contract to R to P. But going this way, so we start with the maximal ideal here. We can contract from here, from this corner to this corner, in two different ways. You can contract like this or contract like this. We would get the same result. And so contract like this, we would get PRP and then P, and contract like this, we'll get some Q and then to P. Okay, so contract maximal ideal of R mod P, R minus P inverted in S to get Q in spec S such that Q contracted to R is P. So this is the, and as we mentioned earlier, the last part says that the map is surjective. Okay. So we will stop here, and we will continue in the next lecture with start with proving what is called the going up theorem, and which is a statement about chains of primes, how they behave in an integral extension.